I'm gonna go ahead.
I'm going to explain the math behind the pendulum, and Eliana's going to explain our design.
Cool.
So the basic formula for pendulum is T equals 2 pi times the square root of the length over gravity. And then when you solve that for the length, it's approximately equal to gravity times T over 2 pi squared. And T stands for the time it takes for the pendulum to complete one oscillation. And to get T, you want to do 60 because it needs to complete in 60 seconds over the oscillation. And the
What's the 60 seconds? Could you remind us? Because I know you guys did that with the calculations, but
the original pendulum that we saw the video of came back into sync after 60 seconds.
okay.
So if you do it at 1 minute, which is 60 seconds, and so if you do 60 over the oscillation for T, then you get then you make sure it's getting back in sync in 60 seconds. And they said that the smallest oscillation was 51 and the largest was 65.
Okay. So, and those are in 65 seconds?
Those are 51 times.
Oh, okay, so it has 51
It'll do
oscillations in 60 seconds.
Yeah.
Okay, gotcha. So which one does the 51?
This one will do the 51 and this one does 65.
Okay. Cool. All right. All right. Is that all the math on it?
That's pretty much the basics behind the math.
Okay, and you guys have a pretty serious spreadsheet that you used here?
Yeah.
So what's the deal with that? We'll take a close look at it. It seems to check out. Yep. So what's that about?
And then that's the theoretical lengths, but there's one more piece. Because the pendulum, because you're using 2 strings, you actually have to use the Pythagorean theorem to calculate the final length of the string since it's a triangle.
But that looks like an isosceles triangle, not a right triangle. You know what I mean? So how do you use Pythagorean theorem?
Well, this is 3 centimeters here.
Uh-huh.
And when originally it's straight down. In theory, this should be straight down, but it's going to get curved. So in theory, it's like that.
Mm-hmm.
So the Pythagorean theorem will calculate you the length to here as if this was straight, and then it'll just straighten out to the isosceles triangle.
Okay. Okay. So almost like I'm thinking of like a perpendicular bisector.
Yeah.
So the sides of the isosceles triangle would be like, each side would be a hypotenuse of the right triangle. Okay. Cool. All right, Eliana.
These are copper pins, and so are these. And this is electrical wire component, which is normally used in wiring things. And we found out that if you use the copper pins, you can put them through the electrical wire component, and you can fine-tune the strings.
So you're kind of jumping ahead. Can you describe the process, like what you guys did first?
Well, at first we just had a wooden base and copper wiring and this. And then we had just regular strings through this. And then we found out, kind of like the hard way, that you can't really tune it that well.
So you had the theoretical lengths that Harel was talking about, and then what happened?
Well, we found that there's a lot to do with the lengths, and you have to fine-tune it, because there's a lot of different components that come in for this to work exactly.
Okay, beyond just the theoretical string length.
Yeah.
Mm-hmm.
And so we found that you definitely have to tune it to make it work at all.
So how much are you talking about, like changing those lengths, like when you do this with the cotter pins and the?
Not that much, because you still have to have a similar length, but you just have to tweak it a little bit.
And so it's off a little bit. Then what does the wave look like?
Doesn't work.
Doesn't work. So it has to be really.
Yeah, it has to be very fine-tuned.
Mm-hmm. Okay, nice. All right, you guys want to do a cycle? Okay.